Okay, so today we are covering unit vectors and dot products. This is Monday. Anyway, this is the notes for Monday. I'm recording them in advance just in case tomorrow is a disaster. And basically the way this works is a unit vector has the same direction as your vector, but it only has a magnitude of 1. So it's like the I and j vectors that we talked about earlier. And the way you find them, so if we're looking for the unit vector u that is based on some vector v, then it is equal to, let me make this a little bigger so I can draw. It is equal to the vector v, that's too thick, the vector v divided by the magnitude, which makes sense because it's the same direction. It's just 1 unit long. So if we take the magnitude, the vector, and divide it by its magnitude, then you should get the unit vector. And the formula for this is, so if we're looking at the vector v, last month, before we left, we learned how to find vector v, the components of it. And that, remember, is that you take the magnitude of v, if you know it, and you multiply it times cosine for the x component. And it is the magnitude of the vector v times the sine, oops, that's supposed to be a comma, sine of the angle. Remember we did that? And then you just divide by the magnitude. And as you can see, when you divide each component by the magnitude, you're going to get, what does this simplify down to? It just simplifies down to cosine of the angle, sine of the angle, which makes sense because what you're doing essentially is, remember we had the unit circle and then we did some problems where we had a coordinate and the length of the hypotenuse for that coordinate was not 1, so you went and you used the triangle trig to find, and then essentially you ended up where you realized that after we'd done a couple of them, that it was just going to be whatever the radius was times the cosine of the angle and radius times the sine of the angle. Remember that? So that's what we're essentially undoing that. All right, so the things you have to do is you're going to be given some vector in its component form, and you're going to have to, from last year, so recall from last semester, how do you find magnitude of vector v? Well, it's equal to the square root of the delta x, the change in x squared, plus the change in y squared. Remember that? And remember when we were going to find vector v, if you were given the components, remember that vector v is equal to, remember that was the magnitude of v, cosine of the angle, comma magnitude v, sine of the angle. Remember all that? Okay, so that's where I get this from. Understand? Well, you'll ask me in class if you don't. All right, so here's an example. They give us a unit vector, or actually they want us to find the unit vector, and they give us v. And they give us that v's components are -4 and 1. And they want the unit vector in exact form. So that means we have to go find the magnitude, and our magnitude of u, this is v, is equal to the square root of -4 squared plus -1 squared, which means it's going to be the square root of 16 plus 1, which gives me the square root of 17. And then we're going to go find the unit vector now, and our unit vector is equal to, remember, it's always going to end up being, so it's that, notice it's going to be the magnitude of the vector times cosine of the angle divided by the magnitude of the vector, right? So that means if I know that the x is -4, then this is going to be negative 4 divided by square root of 17. And the y component is going to be negative 1 divided by square root of 17. But you've left radicals in the denominator. Remember, we're not supposed to do that. So what we end up doing is we have to rationalize it. We have to get rid of the square root by multiplying by the square root both top and bottom. Remember that? We're multiplying by 1 in one of its many costumes. And then when you multiply the square root of 17 times the square root of 17, you get 17. So this is equal to negative 4 square root of 17 over 17. And then it's going to be, oops, that was only the y component. Hang on a second, let me just lasso this and I can move it all. Well, actually, I should move all of it. There we go. Need to move this down because I forgot my y. I left it off. That's okay. I can get to take care of it. So then it's comma. We have negative 1 over square root of 17. And we have to multiply it by square root of 17 over square root of 17. And now we can finish it. Move this back over. And as soon as it behaves, we get negative square root of 17 over 17. And we did this same kind of thing back when we did remember our right triangle trig stuff. So if this is negative 1 and negative 4, if we're looking at the coordinate system, here we go. Remember our coordinate system? If we take this, we're just going to do this off the side. And I go and I put a triangle down here. Negative 4, 1. It's a right triangle. This is negative 4. This is negative 1. And we already know that this is square root of 17. Remember that? So we know that there is some angle in here. Theta, right? And if we're trying to find that, we would use those three, remember that? But we would, when we went to find sine and cosine from this, we can see that from this, that for this, sine of the angle is equal to the y component, which is negative 1 over square root of 17. Remember when we did this? Cosine of the angle is negative 4 over the square root of 17. And is that going to get us to the same place? That was essentially getting a unit circle. I mean, the unit vector. Same math. But now that we know these formulas and we are using vectors, you don't have to draw the picture anymore. You can just go straight and use the formulas. But you have to memorize them. But it's just using something you've already done before, hopefully, if you did your homework. The next thing we have to do is dot products. There's dot products and cross products. We're only going to talk about dot products. So basically, if you end up doing any engineering, you need it in physics. I'm not sure anywhere else where you need it other than mathematics, physics, and engineering. But a dot product is referring to a operation between two vectors. And the dot product, you're just going to take. So I'm going to give it terms of what they gave us. They gave us the x for A is A1 and the y for A is A2. So the dot product is A1 times B1 plus A2 times B2. I personally prefer x's and y's. So this is the first x, this is the first y. Oops, first y, right? For our first point, which is the A. And then this is the second x and the second y. Oh, hang on. These are vectors. I like to do this because this is more like what you did the notation you're used to from finding slope. That's why I prefer it. And basically when you do this, it's the same thing, only it's really easy to see that you are multiplying the x components and adding them to the product of the y components. Well, that's why I like this better. Because it's using something you know, which is you're understanding 2 points and then an x1 and an x2. So basically you're adding together the components products. So you're adding together the product of the x's and you're adding to the products of the y's. So if we do an example for them, so if this is A, if we want to find, and remember this textbook uses a bold A for their matrices, we can't bold our, well we can, but it's hard to do. It's easier for us to write it a little mark on top to indicate it's a vector. And the dot tells us that's not a multiplying. When you're talking about vectors, it's a dot product, which is that operation we just did. And it's going to be, okay, actually, well, we're just going to multiply the x's. So it's 5 times negative 3. That's x1 times x2. And then we're going to multiply the y's. And we're going to add that to it. So then we have 1 times 15. Well, that ends up being negative 15 plus 15, which that equals 0. And here in a little bit, I'm going to show you why that's important. And when you're doing dot products for physics and in engineering and mathematics, that's important. We'll get to it. Okay, here's another one. So for me, it doesn't matter whether it's U1 or U2 or what it is. I'm always going to take the x's and multiply them, and the y components and multiply those. So the dot product of the vector u and v is going to be 4 times 8 plus 5 times a negative 6, and that equals 32 minus 30 equals 2. And that has meaning too. It's, well, sort of. Okay, so that's the dot product. And then we can use that dot product, and the reason it becomes really important and why I used it in summer school when I did graduate work, because I was dealing with vectors and I was doing mathematics on it and doing some really fancy schmancy stuff in Excel. And so I had to find angles between vectors because we were doing all kinds of vector operations, all the mathematics behind it, which that's physics and engineering. All right, so if we want to find the angle between those two vectors, because remember when you were drawing those vectors and you were finding the resultant for it, there was an angle associated with it. Remember back when we were doing our right triangles and all that stuff? Remember there's an angle associated with all this stuff. So if we look at it and we want the angle between between two vectors, we did a little bit of that I think before, but this is really specific to vectors and it's using what we've already learned. And oh, one thing on the notation. I remember this book uses the single bars. I prefer double bars when you're working on it. Why? Because I want to make sure you know that it's not an absolute value. It's actually a vector operation. Remember? Double bars. Okay. And then we can find that angle by taking the dot product of vector A and B and then dividing by their magnitudes, the product of their magnitudes. So if we want to solve for this angle, remember how we solve for angles? We have to do the inverse of it. So that means that to find that angle, we have to find the inverse cosine of that dot product divided by the magnitudes. Okay, that's going to be hard to see, so let me go up a little bit more. There we go. All right, so you know how to find dot products now. It's really easy. Multiply the x's, multiply the y's, add them together. Divide by the magnitudes. That's just the square root of the delta x plus the delta y squared, right? So you find the magnitude of A, find the magnitude of B, find the dot product of the two, and then you plug it in, punch the calculator, and you get the angle between. So let's try one. In this case, we want this angle. Now, you have to choose a mode, and that wasn't said here, but it should have said in degrees. In degrees. They are assuming it, but that is not a good assumption. You need to set your calculator in degrees if you're going to do this. Because we could do this in radians as well. So we're going to do it in degrees. So first we're going to find the magnitudes, because that's really easy to find. And then we're going to find the dot product. So the magnitudes we learned before Christmas. So the magnitude of u is equal to the square root of the delta x's. And the delta x's for u, that would be 5 squared. Hang on, I don't need, there are no negatives, so I don't need a parentheses. 5 squared plus 1 squared. Take the square root. And that's equal to the square root of 26, because it's 25 plus 1, which is 26. And I just want to point out something to you, because we'll need it later. This is equal to 13 square root of 2 if we simplify it. No, it's not. I'll tell you in a second. It's square root of 2 times the square root of 13. And we'll get to why that's important in a second. Then we want to find the magnitude of v. And now I'll give away a secret. So for v, it was negative 2 and 3. So we need negative 2 squared plus 3 squared. Take the square root. So that's 4 plus 9 means it's the square root of 13. Now you see why I wanted 13s. So you have, look, this is 1, this is 2. Got it? That's why I did that. And you'll see in a second why that's important. All right, and then now I want the dot product, so I want u dot v, the vectors, and that's going to be the x's. So that's going to be 5 times negative 2, product of the x's, plus the product of the y's is going to be 1 times 3, which means that's negative 10 plus 3 equals negative 7. So now we can go find the angle. We're just going to plug it into the formula up above, that one right there. So we're going to go theta equals cosine inverse of the dot product, which was negative 7, over the magnitude of the first one, which is square root of 2, square root of 13. And then the second one would be square root of 13. And why did I show you this? Because if they want you to do this without a calculator, you need to know that the square root of 13 times the square root of 13 is 13. Now, for your purposes, you're just going to have a calculator, so you just plug it in. But I just want to show you a little number sense, because you're going to need it for calculus next year. And we end up with a negative 7 over square root of 2, times 13. Because the square root of 13 times square root of 13 is 13, so it's 13 square root of 2. 2, not 3. And then you're going to punch it in the calculator. In this case, we would rationalize if we wanted an exact answer. But so it's 112.380 degrees, if you round it correctly. All right. Now that we've learned to find a dot product, we've learned to find the angle between, the next question is, are things orthogonal? Now, you don't want to have to go calculate that angle every time, because that's a painful thing to do. There's a quick trick to figuring out if something's orthogonal. And orthogonal means it's perpendicular. And perpendicular means it's a 90-degree angle, which that becomes really important, because cosine of a 90-degree angle is 0, right? That means that the dot product is 0. Okay? Does that make sense? Because remember our formula back up here, it's cosine of theta, and it's the dot product over the magnitudes. Well, the magnitudes of the things, they're not 0, but the dot product is 0 if they're orthogonal. So we look back at our examples. Remember I said I was going to get back to this? Oh, look, right here. Right here. For A dot B, is it equal to 0? So does that make it orthogonal? Yes. But whereas when we did U dot V, we got 2, which is not equal to 0. So that's not orthogonal. So the way your problem would work is you would be given this. You'd be given that first, and you would have finished up that problem with the next part, which is the orthogonal. So we're just going to pretend we were doing it and we're finishing it up. So if we were finishing 2A up, we would write that the dot product of vector A and vector B is equal to 0. So vector A and vector B are orthogonal. That's a mouthful. Orthogonal. And for 2B, U vector dot V vector is equal to 2, which is not equal to 0. So I expect you to tell me it's not equal to 0. So U and vector V are not orthogonal. And this is an important skill to know for when you do higher mathematics, engineering, and physics, because they're going to ask you these questions and they expect you to be able to do the math to show why something is perpendicular or not perpendicular. And that's the notes for today. And I got them done so that just in case we have a bad day, y'all can watch the video and get the notes.